All right. Okay, we're about to hear from Milagros Izqueirdo from Linköping University. Let's hear about one-dimensional families of Riemann surfaces with automorphisms. And as a reminder to everyone here, please do mute your microphones during the talk. And Milagros, are you willing to take all your questions at the end? Is that how we'll do this?
Yes.
Okay, then. Questions at the end.
Okay, so I will talk about the one-dimensional families of Riemann surfaces with automorphisms. So I will talk in dimension 2 and not 3, but I will see Riemann surfaces and families of Riemann surfaces as Hurwitz as orbifold covering space of the Riemann sphere. So I hope I will have a flavor of what is happening in three-dimensionals and knots and some of the things you have down there. And well, that is when I'm thinking about the Riemann surface. A Riemann surface for me will be a one-dimensional complex manifold, where the important thing is the field of meromorphic functions. And the field of meromorphic functions will be generated by two meromorphic functions, x and y. And we know that they satisfy algebraic conditions. So there is a polynomial in x and y given the field over the field of the complex projective line, which is the Riemann sphere. But as I want to see it, and is that allows us to work as Riemann surfaces, as orbifold coverings of the Riemann sphere, is to see then, and I'm only working with Riemann surfaces of genus at least 2, is to see them as the quotient of the hyperbolic plane by a Fuchsian group. And a Fuchsian group is a discrete subgroup of the group of hyperbolic automorphisms. Well, and in such, it works properly discontinuously. And its group that works in a properly discontinuously on the hyperbolic plane, in this case, will have a fundamental polygon for the action. And Poincaré showed, in fact, rigorously masked that if we have not only that each Riemann surfaces is uniformized by of genus at least 2, uniformized by a Fuchsian group, but that if we have an hyperbolic polygon and we have a good side pairing, and a good side pairing, it means that the area of the polygon and, well, the pairing has to be that we consider the pairings as the generators of a group of hyperbolic transformations. This group has to be discrete, and we want to be hyperbolic, so we have to have some conditions about the boundary of the polygon to have a good area. But so what Poincaré said is that if we have this polygon and we consider pairings in the boundary of the polygon as hyperbolic motions, and they generate a group, this group is a Fuchsian group. And of course, the fundamental polygon for this Fuchsian group is again the polygon. So we can see the polygon with identifications on the boundary exactly as one Riemann surface. In fact, a marked Riemann surface, so you will have even a certain geometry. And two such Fuchsian groups are conjugate in the PSL2R if and only if, in fact, we have one hyperbolic motion moving the fundamental polygon for the one to the fundamental polygon for the other. I won't consider, except for a very special kind of surfaces, I won't consider them as that a Riemann surface, if it is compact, will be in fact a complex plane curve. And then, in fact, the field of meromorphic functions of the surface is exactly the field of rational functions of the curve. Well, but this is the sample is in fact is original Klein a sample from 1879 and is Klein's quartic that I have given here the equation of Klein quartic, not the typical equation x3y plus y3 plus x equal to 0. That is why it's called Klein quartic. But the equation is a 7-seated orbifold covering of the Riemann sphere, ramified on 3 points of the Riemann sphere, and that this is y to the 7 means that is a covering of degree 7 of the Riemann sphere, and is ramified on we see here that it's ramified on the 0, the 1, and the infinity on the Riemann sphere. And this is why I will see all the Riemann surfaces, so a la Hurwitz, as ramified Riemann coverings over the Riemann sphere. So it's orbifold coverings of the Riemann sphere. And I said I'll not consider as curves, but it's that one case, and is when the curve is in the case of Klein's quartic is defined of a field of number. And in this case, the Riemann surface of the complex curve X will be defined as covering map beta, which is called the Belli function over the Riemann sphere, with the conditions that it has to be ramified at most 3 points. And we know that these 3 points can be chosen to be the 0, 1, infinity. And in fact, this is what is happened on we said, on Klein's quartic. And in fact, Klein's quartic is defined over the rationals we see here. So this we have a decomposition given by the Belli function beta on the Riemann sphere, which is called the design the Enfant. And the design the Enfant, what it will do is allow us to embed a graph in the surfaces. So the preimage of the 0 provides the vertices, the preimage of the 1, that was 0, 1, and infinity, or the ramified points. The preimage of the 1 will give the edges, and the preimage of the infinity will be the surfaces. In fact, the center of the surfaces. And this is the tessellation and how one puts the graph on Klein's quartet. And of course, I said that Klein's quartet, to be Klein's quartet, we have to have here a pairing which is known to most of you. So, and not say, but for me, what is important when we have a Belli curve or a Riemann surface, which is a covering of the Riemann sphere ramified on 3 points, is automatically we can see the Belli function, which is meromorphic, so it will be an orbifold covering, and I will see the orbifold covering of the X is uniformized by a surface group, which is, I will call it very abstractly gamma G. And of course, we have the covering from the curve X to the quotient given by the by the action of the group of automorphisms, which I haven't said, well, I have said here, the group of automorphisms of the Riemann surface X, and the group of automorphisms in the universal covering H will lead to a fusion group, and it is ramified. And of course, the quotient is the sphere with three points. So this fusion group has to be it has to be a triangle group. And this is and of course, as always, and we have an orbifold covering, we will have the monodromy of the covering, which is the representation of the uniformizing group of the quotient, the triangle group, in the group of automorphisms, which is, for the case of Klein's quartic, is the PSL tool set. So again, now I will see Riemann surfaces as quotient spaces of the hyperbolic plane by a group of discrete subgroup of the group of hyperbolic motions. So I will see again Riemann surface of genus at least 2 as the quotient of the hyperbolic plane by a fusion group, and I will allow it to have singular points. So really, I see it as a orbifold, hyperbolic orbifold, not as a surface. So the fusion group delta will have generators A1 to B8. That will be the genus of the underlying Riemann surface, which is X. And then they will have also elliptic generators, X1 to XR. And this elliptic generator is given one of the branching points in the quotient, which of course they are called cone points because it's the. And everything we will put it in the signature. I will call the signature of delta is H, again, the genus of the underlying topological surface, and the orders of the different classes of conjugated classes of elliptic elements, maximal. And as we said, that a fusion group has always the fundamental polygon, fundamental region, the area of any fundamental region will be the area, we will call it the area of the fusion group, and this is just to calculate the area, if you want, is 2 pi minus the Euler characteristic for the orbifold. And of course, we can see again the fundamental, as we said, the fundamental region is together with the pairing as our Riemann surface X. They will have absolutely the same hyperbolic metric. When we want, I'm talking about orbifolds, but of course, when we want to do automorphisms, we need then to have torsion-free. And Moore in 1976 proved that any Riemann orbifold is conformally equivalent to a Riemann surfaces without cone points. But this is conformally equivalent. We have to forget the marking. And here there are three examples of such orbifolds. One is the sphere with 4 cone points, 3 of order 2 and 1 of order 4. The third one, then to the right, is a Riemann surface, in fact, of genus 5, which is given by this polygon, and we are representing the pairings that generate the uniformizing fusion group. And the one in the middle is the very well-known modular space, which is the space of tori. And we know that this is the quotient of the hyperbolic plane by the modular group, the PSL2 set. which is generated, we can consider that is generated by the parabolic motion. Zeta is going to zeta plus 1, and the involution that taking zeta to minus 1 zeta, which is that has the I as a fixed point, or the product of the parabolic and the involution is given a rotation of order 3. Zeta is to zeta minus 1 over zeta. That fixes the cubic group of the unity. And this is a Riemann surface, but it's not compact because, of course, we have a puncture, is the infinity. And if we want to fill that puncture, we have to allow nodal curves. And in these curves, the nodal curve is the very well-known curve with equation y squared is equal to x cubed. And again, we said we will see Riemann surfaces as orbifolds given by an holomorphic functions as orbifold coverings given by so the quotient of the hyperbolic plane by a group lambda will give the Riemann surface, and we have an holomorphic function to another Riemann surface y, which will be given by the uniformizing group delta. And we know that we have there is because we have the covering, we have an automorphism, a monomorphism, a way to include lambda in delta. And the way we include lambda in delta, in fact, will give us the classes of covering. And then we also know that that will be given by the monodromy, which is the representation of the group delta in the symmetric group on the cosets of lambda in delta. And we can see lambda as the preimage of the stabilizer of the digit 1. And I said that because if I consider Riemann surfaces, X will be connected, so the action of theta will be transitive. And of course, we can set its symbol, that is a coset. It will be a seat for the covering, and of course, it will be a fundamental polygon for theta. So what we are saying here is that we have the fundamental polygon for delta, and theta is telling us how we have to paste the fundamental polygons for delta to get the fundamental polygon for x from lambda. And it's important now that we are getting, just there, we are getting a tessellation. And when we are getting the tessellation, we are automatically setting a graph within the Riemann surface. And in fact, this graph, which in the case of the Sand-Danfans, is the Sand-Danfan, this graph is the dual of the Schreier-Reidemaster coset graph. And it's telling us, in fact, again, how we are setting lambda in delta. So David Singerman in the 70s give the structure theorem, in fact, how I and theta. So if we know delta and theta, which is I, we automatically know the structure for lambda. Not only the structure, sort of topology, we have more structure also for the conformal structure. And now we are interested, because we are interested in group actions, we are interested forget about that. Look at the end of that. We are in fact interested in regular coverings, regular branch coverings. So in the beginning, we take the branching, which will be BG on the T, which is the quotient orbifold, and we just consider the unbranched covering. That will give us a way of setting, and this is regular way of setting the fundamental group for X as or the orbifold as a normal subgroup of the fundamental group of the orbifold. Well, and now they are surfaces because are branches, but what we have is that we can also compactify. So again, this theta is giving us the monodromy of the covering from X up to the quotient by the group G. And in fact, we can see again, this delta is the lifting to the universal covering of the group G. And of course, if we have an automorphism of the finite group G, two monodromies, which is just the one composed with the automorphism, will give us exactly the same covering, even the same, everything is the same. And if we have the same coverings, but with two representations, we will get the automorphisms alpha of the finite group. So when we want to study, we will study, in fact, classes of epimorphisms of monodromies theta up to automorphism of the finite group G. And this is how will we see it now. So if we have an orbifold covering or an holomorphic map from now, I will consider when I write the gamma that this gamma is a torsion-free fusion group. So I have really the fundamental group of Riemann surface, or with surface, of genus, some genus G, and I'm going to and this is a covering, and the quotient is uniformized by a group delta, that in the group delta, we can have ramification. So again, the group delta, as we said before, is a fusion group, so it will be given the generators, the alpha 1 to beta H will be the generators for the homology group, the fundamental group of the puncture surface, and then we are putting cone points, each of them of order M1 to M and R. And if we are considered the monodromy theta, what we are having is the action again of the delta in the classes of gamma to delta, but we know that this coset, the monodromy group will be exactly the group G. So, and it has to be an epimorphism, so it has to be the group G. So what we want is that this list of elements of images, theta of alpha 1 to theta of gamma R, has to generate the group G, and we will call it a generaton vector. Of course, again, if we are pasting the order of G polygons for delta to get the polygon from gamma, we had to have the corresponding relation, the Riemann-Hurwitz relation for the areas, and this is given us also the genus of gamma. And again, so what we are interested in are in list of possible generators for the group G, and we are interested in the conjugacy class. And then we want the generators, they have to be generators, and this is what we will call it K0 of G. But again, we are not interested in the epimorphisms and the possible list of generating vector. We are interested in up to automorphisms of the finite group G. And this is what we call tilde K O G. And what we are interested in is in strata, which are complex one-dimensional in the Teichmüller, in the moduli space of that. And we had to first consider the Teichmüller space. So we will consider abstract fusion group, and we know that the Teichmüller space can be with zeta all the markings, which is the way of setting. So include the group gamma 0 in the PSL2R, then said that it has to be injective and discrete. And of course, as we said before, we have two polygons and we had just one motion of the hyperbolic plane taking the one to the other. It will be the same geometry. So we are having it modulus the hyperbolic motions. We can give the Fenchel-Nielsen coordinates using pair of bands, and then we see that the Teichmüller space for the surfaces of genus G is homeomorphic to the complex ball of dimension G, 6G minus 6, and also that this space, in fact, is an analytic space of complex dimension 3G minus 3. And on the exactly as when one have tori, the space of tori is given by the hyperbolic plane by a group of diffeomorphisms of the hyperbolic plane, which the hyperbolic plane is the Teichmüller space for the tori. In the same way, we have the modular group, which is the modular group is the classes of orientation preserving diffeomorphisms of the surface X, modulus the diffeomorphisms which are isotopic to the identity, which is in fact the outer group of the uniformizing group of the gamma G of the surface X. Also, the Teichmüller modular group, I will call it the modular group because it acts as the usual modular groups, the classic modular group. So I will forget the Teichmüller. So the modular group will act on the Teichmüller space in a discontinuity, and the space, the Gaussian space, is the moduli space. One can prove, and we have the uniformation theorem for orbifold. So what we have here is the moduli space seen as the just the Gaussian of the universal covering, which is the Teichmüller space by this group of the modular group. And as an orbifold, it will have an stratification as orbifold, and it's of course its strata in the orbifold stratification will be given by the surfaces which has certain isotropy group, and Nielsen conjecture proved by Kerckhoff shows that for G at least 3, it's straighter in the stratification will coincide with exactly the surfaces that has a particular determined action of a finite group G. So what Each strator, it corresponds to a conjugacy classes of finite groups, finite subgroups of the mapping class rules. Is that for surfaces of genus 2, that all surfaces of genus 2 are hyperelliptic. So one requires for the branch locus of the surface in genus 2 that they are the surfaces that have more automorphisms than just the trivial and the hyperelliptic involution. And this we could do with any subspace of the Teichmüller space. In the same way, if now we have an abstract fusion group with certain signature, again, we consider the Teichmüller space of this signature with all the ways to, all the markings, which is all the ways to set this group delta as a group of hyperbolic motions in such a way that is discrete. And again, in the same way, just by pinching a curve, one can see that this space is homeomorphic to a ball of dimension 6h minus 6 plus 2r. And in fact, it has a complex structure of dimension 3h minus 3 plus r. And again, if lambda is a subgroup of delta, the inclusion of lambda in delta induce an isometric embedding of the Teichmüller space for delta in the Teichmüller space for lambda, which is the one aspect. Again, if one considers the outer automorphisms, the outer group of delta, which is again the orientation preserving the pheomorphisms, modulo the ones they are isotopic to the identity, one get that this group adds discontinuity on the corresponding Teichmüller space in the way that everyone expects, and we get, in fact, the corresponding moduli subspace. And this moduli subspace will be a union of a strator in the stratification, the orbifold stratification of the moduli space of surfaces of genus G. And again, we are always talking about orbifold coverings and orbifolds. This group delta is the orbifold fundamental group of the orbifold the hyperbolic plane uniformized by delta. And here is to say again what I have said before. If we consider the action of a determination given by this delta of the of a group, finite group of a group of as a group of automorphisms of a surface of genus G, we see that this group, we have this space of the automorph in the Teichmüller space, and this, in fact, this TGG is a subspace of T delta, because remember in T delta we allow the same signature, but they can have different options. And of course, again, so we have, if we have something in the, and this is very important, I want to that in fact this G is the union of different strata. So each strata will be given by a particular theta, and we have to control to have all then. and brought also that this orbifold stratification is in fact an stratification also for the algebraic structure. And so now we are interested in these strata, which are given by a determined action given by theta of a group, finite group G on surfaces of genus G. But of course, we had to see it when one makes sees then really we begin by actions theta, and in actions theta we will have the action where the G is the full automorphism group of the surface, but we have also to put together, and this is why we are getting the cluster, surfaces that admits more automorphisms than just the G. Again, we are, and this is important, we are working with signatures. So now I will change a little and I will call GS is a abstract group with signature S, and TS will be the tachymular space for groups with this signature. And again, MS will be the modular group for groups with that signature, and the space in the moduli for groups with that signature. And the first thing we have to do that is to have this fiber bundle, which is just the, we will consider in this S of markings in the markings sigma in the tachymular space and classes of generator vectors. And of course, when we have that, we see that in fact, each element, each point in this space HGS corresponds uniquely to a conformal equivalence class of orbifold coverings. H on the kernel, the marking of the kernel, on the marking of the G. And this is what we are using. That this we have a point here. So a point here corresponds exactly with a universal covering of that. Sometimes we have some problems, and this is what we call the modular companions, and is if we have so the surfaces, they have the same universal the same quotient. They are conformally equivalent, but up they are not conformally equivalent. So somehow we have auto intersection or some problems with the strato. And now just very fast, because I have like 2 minutes. The one-dimensional strata, because we are interested, because the one-dimensional strata will be Riemann surfaces itself. At the case of the modular space, the space of torides is a Riemann surface itself. In fact, is the Riemann sphere with a puncture and 2 cone points of order 2 and 3. This is what we have seen. And so if we want one-dimensional strata, it has to be either that the quotient is the sphere with 3 branch points, or the quotient is the torus with 1 branch point. So, and if the quotient is the sphere with 4 branch points, we will have the covering, the orbifold covering from the surface S to C, and the monodromy of the covering will be given by how we put in the group G, as always. And so again, we take away the branching, and then what we have is this the fundamental group will be generated by the meridians around there. And of course, we always can consider, and this is the important things, we can always consider that we have branches about 0 over 0, 1, the infinity, and another point lambda. And now we are interested in the conformal structure of C lambda, because it's what we have in the quotient. We know that the conformal structure of C lambda, it depends of lambda. And in fact, the C lambdas form the Riemann sphere minus 3 points, the 0, 1, and the infinity. So they are, we have dimension 1 conformal structure. And we see that the fundamental group of B lambda will act. So what now we can see is if we have the twist around given by the beta 0, beta 1, and beta lambda, the fundamental group of this, the sphere minus the 3 points will act there, and this and it will also act on the space of the classes of the generating vectors, and then it gives us the straton S as a orbifold covering of this beta, which in fact is ramified over 3 points. And of course, we have to take them away. So the H0, H1, and H infinity are the punches, because they are the number of primitives over the 0, 1, and infinity. And again, with Riemann Hurwitz, we are getting the genus of the surface. And well, we have an example about about this. The predicted Riemann surfaces of genus G, they appear for all genus that has an action which of this is unique of the dihedral group of order 2G plus 2, direct the C2, and we can see in fact that this covering is in fact is an isomorphism. So this family is in fact the Riemann sphere without 3 points, but in fact the one corresponds to a ramified point of order 2, which is the Akola-McLachlan surface. So there we have an example of modular companions. Of course, if one has, if one allows that can have generators can go to the same conjugacy class, then we have to do the quotient by the corresponding subgroup, then the group of that preserves that the cross ratio. And we have another example, in this case, the samples of, for an infinite number of genus, of genera, the families that the Riemann surfaces that admits 2 different pigonal morphisms. And again, we are getting that the covering is an isomorphism, so we are getting the sphere. And the same way we can do when the covering is the quotient is the torus with the compoints of order n. We have exactly the same. Well, this as we always have to work with full automorphisms group, we have to be careful that we don't extend, but we know exactly when we can extend, and then it will be of the first type we saw. So now we are saying that the eta of alpha is, there is not an automorphism of G, taking eta of alpha to eta of alpha inverse and eta of beta inverse, and then again, well, this is a case, and again we will have, as before, the action of the fundamental group of the torus with a point, with a point on the monodromy we have for the surface S. So I'm using the monodromy in two different ways. And well, good that the forgetful theorem says that we can forget where is that point, the cone point. So that fundamental group, the modular group for that will be the modular group of the torite. And again, we have to see how this the fundamental group of this orbifol acts on the modular group, and this is a given, and we see that is so, and we have everything. Very important, we know that x2 equal to y3, it doesn't act as the identity. It's something of order 2, and again, we have absolutely the same covering. And again, but in this covering, as we forbid this taking the inverse, it will work that x2, y3 will work will act as the identity. And then we have exactly the same theorem. We have to take the preimage of the x and y and the infinity. And with that, we are getting the number of punctures, the number of cycles over x, over y, and with Riemann-Hurwitz, we can calculate the genus. And well, this is one example, but I just wanted to say that very important, and is what I talk about. All these stratas are in fact belly curves. And we know nothing. We know that it's belly curves, and all the samples I have put, they were belly curves of type 2 infinity. And well, we don't know which belly curves appears as one-dimensional cosymmetric. In fact, we know nothing about the belly curves we are talking. So we would like to know much more. Thank you.
All right.